Okay, good day everybody. Welcome to our next episode of the Dissection of the Human Brain. I'm Dr. Sanjay Sanyal, Professor and Course Director of Neuroscience, and the camera person is Mr. Mark Lessard, our IT Administrator. Today I shall demonstrate all that we need to know about the cerebellum. So what you see in front of you, which I'm holding, this is the cerebellum attached to the brainstem. First, let me give you a quick overview of how the structures are disposed. This is the medulla, this is the pons, and this is part of the midbrain. The rest of the midbrain was been removed while it was being removed from this cadaver. And if you notice that this is the anterior part, and stuck to the dorsal aspect of the posterior part of the brainstem is the cerebellum here. This whole thing is the cerebellum. So therefore, the cerebellum is attached to the dorsal aspect of the pons and the medulla. So this is the orientation of the cerebellum in the lateral view. This is the orientation of the cerebellum in the anterior view, and this is the view of the cerebellum from the posterior aspect. Now that we have seen the orientation of the cerebellum, now let's see how the cerebellum is located in situ in the cranial cavity. For that, I need to show you the cranial cavity itself. This is the base of the skull, and this is the posterior cranial fossa. You can see the cerebellum is located here. The cerebellum sits like this. Therefore, this depression that you see in the posterior cranial fossa, these are known as the cerebellar fossa. And this groove that you see, this is where the tentorium cerebelli is attached. So therefore, this is the infratentorial compartment which houses the cerebellum. This is the foramen magnum through which this medulla passes out. So this is the orientation of the cerebellum. So now that we have seen how the cerebellum is disposed in the cranial cavity, we understand immediately something. The cerebellum is like a thick disc. It has got a superior surface, it has got an inferior surface. The superior surface is the one which is separated from the occipital lobe of the brain by the tentorium cerebelli. So therefore, the tentorium cerebelli is here. And the inferior surface, this is the inferior surface, which is the one which is resting on the posterior cranial fossa, infratentorial compartment, or the cerebellar fossa. In fact, if you look at the cranial cavity much more closely, you might see some grooves on the floor. Those are known as the brain markings caused by the cerebellar grooves. In this particular specimen, they are not so obvious. So this is the orientation of the cerebellum. Now let's take a look at the parts of the cerebellum. The cerebellum has got two hemispheres. We are looking at the cerebellum from the posterior aspect. So this is one hemisphere, this is one hemisphere. And joining the two hemispheres, we have a midline structure, which you can see here. This is the vermis. Now, quite often students have asked me this question: is the vermis like the corpus callosum of the brain? No, the simple answer is the vermis is not like the corpus callosum of the brain. The vermis is got the same structure as the cerebellar hemispheres. Only thing is it has got less of the cortex matter, which we shall see a little later. It is not like the corpus callosum. The corpus callosum, on the other hand, is a thick sheet of white matter which joins the two cerebral hemispheres. So therefore, vermis is not the same as the corpus callosum. Now let's take a look at the surface, the appearance of the cerebellum. For the sake of description, what I have done, I have removed the pia mater. Otherwise, the pia mater is the one which covers the surface and which has all the blood vessels, and therefore, unfortunately, by removing it, we have also had to remove the blood vessels. But we immediately notice that the cerebral surface has got multiple grooves. The purpose of this is to increase the surface area of the cerebellar cortex. And each individual structure fold that you see here, they are referred to as the cerebellar folia. The single purpose is to increase the surface area of the cortex. And as a result of this, the cerebellum, though it is tightly packed in such a small compartment in the posterior cranial fossa, it has got more number of neurons than the cerebrum, which was contrary to what was known earlier. In fact, the word cerebellum means little brain. Previously, it was thought that it's a small brain, it's a little brain, it's silent brain, but now as more and more research is being done, it's being realized that the cerebellum, in fact, perhaps is even as important, if not more important, than the cerebrum itself. Okay, that's so much for research. Now let's take a look at the fissures and the lobes, the anatomical lobes of the cerebellum. If we look at the posterior border of the cerebellum, the one which is abutting against the occipital bone, the posterior border, there is a horizontal fissure here. So this is the horizontal fissure. We can see it clearly here. This is the horizontal fissure. It's a very deep fissure. And this horizontal fissure runs on the posterior aspect, and it divides the cerebellum into a superior surface and an inferior surface, which we have already alluded to. So this is the horizontal, the fissure. Now let's take a look at the superior surface. We see a V-shaped fissure here. This fissure here. This V-shaped fissure divides the cerebellum into a V-shaped anterior anatomical lobe, and the rest of the cerebellum, partly on the superior surface and partly on the inferior surface. The whole thing is referred to as the posterior lobe. Some books also call it the middle lobe. So this is the anterior anatomical lobe. This is the posterior or the middle lobe, which extends from the superior surface to the inferior surface. And finally, I'm going to turn the cerebellum over like this and turn it around like this. We see another fissure deep here. To show you better, this fissure. This fissure. This is known as the uvulonodular fissure. And this demarcates one small lobe of the cerebellum, which is referred to as the flocculonodular lobe. And this is the flocculonodular lobe. So to repeat, superior surface, we have the primary fissure, anterior anatomical lobe, the middle or the posterior lobe, and finally on the inferior surface, anteriorly, we have the uvulonodular fissure demarcating the flocculonodular lobe. So these are the anatomical lobes of the cerebellum. Now, traditionally, this anatomical lobe used to be referred to as the spinocerebellum. However, that classification has changed somewhat. I'm going to tell you the new classification just now. The anterior anatomical lobe was referred to as the spinocerebellum because it received maximum connections from the spinal cord. The middle of the posterior lobe used to be referred to as the neocerebellum or the cerebrocerebellum, and phylogenetically the newest part of the cerebellum because it has got extensive connections with the cerebral cortex. And the flocculonodular lobe is the phylogenetically the oldest part, and this is referred to as the vestibulocerebellum. Now what we'll do, we will classify the cerebellum according to its current functional classification. For that, I have to include the vermis also in my description. So the current functional classification is as follows. This is the region of the vermis, the midline vermis. It extends from the superior surface and goes all the way to the inferior surface. There we see the vermis deep inside. So this whole vermis is referred to as the vermal region or the spinocerebellum. Vermal region or the spinocerebellum. This whole vermis is concerned with controlling the axial or the truncal musculature and the proximal limb musculature. Now, if we look just on either side of the vermis, approximately where my index finger is located on this side and approximately where my index finger is located on this side, again extending on the superior surface down to the inferior surface. That portion is known as the paravermal region because it is on either side of the vermis. It is also referred to as the intermediate part of the hemisphere, here and here. This is also the spinocerebellum, but this is concerned with controlling the tone of the distal musculature. The distal parts of the limbs, their muscle tone is being controlled. Then we have the remaining part of the cerebral hemispheres, this whole thing here and the whole thing here. This is referred to as the cerebrocerebellum or the neocerebellum or the pontocerebellum. This is the, as I said, the phylogenetically oldest part of it, and this is concerned with most of the activities of the cerebellum, namely motor planning, coordination, volitional movement, fine-tuning, correction of movement errors. All these things are done by the cerebrocerebellum. And finally, the last functional component of the cerebellum is the same one which I had mentioned earlier, the flocculonodular lobe. This is concerned with posture, balance, and smooth pursuit eye movement, and it is also referred to as the vestibulocerebellum. So this is the current functional classification of the cerebellum. Having said the functional classification, let me give you a quick overview of the blood supply of the cerebellum. Unfortunately, as I mentioned earlier, I had to remove the pia mater, and therefore most of the blood vessels have been removed. But to understand the blood supply, we'll have to look at it with the brainstem in its location. This is the medulla, this is the pons, and this is part of the midbrain. So running from here, from the medulla, one blood vessel goes all the way to the back of the cerebellum on the inferior surface. That is known as the PICA, posterior inferior cerebellar artery. It comes from the vertebral artery and it supplies this area. It also supplies the medulla, but we are concerned with the cerebellum right now. Then there's another artery which is also coming from this location in the pons, and it's coming and supplying the inferior but the anterior part of the cerebellum. That is known as the AICA, anterior inferior cerebellar artery. This arises from, this is the first branch of the basilar artery which runs on the basilar groove of the pons. So this is the AICA and this is the PICA. And finally, supplying the superior surface of the cerebellum is an artery which is arising also from the basilar artery but runs like this and supplies the superior surface. That is known as the superior cerebellar artery. So therefore we have the PICA, the AICA and the SCA. These are the three principal arteries of the cerebellum which supplies the cerebellum, and these three arteries are very important. They produce lots of stroke syndromes of the brainstem, but they also produce cerebellar manifestations. Coming to a quick word about the venous drainage. The venous drainage of the cerebellum is best understood by considering the lateral veins and the median veins, superior surface, inferior surface. So the superior lateral veins, they drain into a venous sinus which is running here. That is known as the superior petrosal sinus. The inferior lateral veins, they drain into a venous sinus which is running here. That is known as the inferior petrosal sinus. Coming to the median veins, the superior median vein, it drains into a vein which runs here. That is known as the great cerebral vein of Galen. And finally, the inferior median vein, it drains into a vein which runs here. That is called the straight sinus. So these are the venous drainage of the cerebellum. Now we come to the next part, the peduncles of the cerebellum, which we can see in this specimen here. The cerebellum, as I said in the beginning, is attached to the dorsal aspect of the brainstem, namely the medulla and the pons, and also to the midbrain. It is attached by means of three pairs of pillars. Each pillar is referred to as a peduncle. And because it is attached to the cerebellum, these peduncles are referred to as the cerebellar peduncles. Let's look at the first peduncle, which is easily obvious in this specimen here. The largest and the most prominent peduncle that we see here. This is the middle cerebellar peduncle. As we can see, it is extending all the way from the pons and it is merging into the cerebellum. This is the middle cerebellar peduncle. This is by far the largest peduncle and it carries most of the input to the cerebellum from the cerebral cortex in the form of tracts which are known as the cortico-pontocerebellar tracts. This is the largest input to the neocerebellum, cortico-pontocerebellar tracts through the middle cerebellar peduncle. This connects the pons to the cerebellum. Having said that, now let me show you the inferior peduncle. If we move the medulla to one side, we notice that there is a pillar which is extending up from here. A pillar which is extending up. This is the inferior cerebellar peduncle. This inferior cerebellar peduncle connects the medulla to the cerebellum. And finally, we have the superior cerebellar peduncle. To understand the superior cerebellar peduncle, I have to show you the midbrain. This is the midbrain. So this is the superior cerebellar peduncle. This side, and on this side, this is the superior cerebellar peduncle on this side. This is the superior cerebellar peduncle. So now let's come to what are the structures which are running through the superior, middle and inferior cerebellar peduncle. Middle cerebellar peduncle I've already mentioned. It is the largest input to the cerebellum and the input is the cortico-pontocerebellar tract, the largest input to the neocerebellum. What about the inferior cerebellar peduncle? The inferior cerebellar peduncle carries the spinocerebellar tracts to the cerebellum, the cuneo-cerebellar tracts to the cerebellum. So these are all afferent tracts to the cerebellum, but it also gives rise to a few efferent tracts which are coming out of the cerebellum, namely the vestigio-vestibular tract, the vestigio-reticular tract, and the vestibulocerebellar tract. They also go through the inferior cerebellar peduncle. That is why the inferior cerebellar peduncle has been subdivided into two components, a restiform body and a juxta-restiform body. The restiform body is the one which gives all the afferents to the cerebellum from the spinal cord. And the juxta-restiform body is the one which brings out the efferents out of the cerebellum, namely the fastigiovestibular and the fastigioreticular tracts. Coming to the middle cerebellar, superior cerebellar peduncle. The superior cerebellar peduncle is the main outflow. The superior cerebellar peduncle is the main outflow from the deep nuclei of the cerebellum. The deep nuclei of the cerebellum, most important of them is the dentate nucleus. The second largest is the globose emboliform nucleus. They all give their outflow tracts through the cerebellum, through the middle cerebellar peduncle, and these structures, they cross inside the midbrain at a structure which is known as the decussation of the superior cerebellar peduncles, and they go to the opposite side, VL nucleus of the thalamus and the red nucleus of the midbrain, and thereafter they go to many other places. So these are the three pairs of peduncles which connect the cerebellum to the brainstem. Okay, so this is the first part of our dissection, and in the second part of our dissection, I'm going to show you the sagittal view. So, if there are any questions or comments, please put it in at the comment section below. Have a nice day. You sir. Okay. Ready? Mm-hmm. Okay, good day everybody. Welcome to our second episode of Dissection of the Cerebellum. What we have done is, we have made a sagittal view of the brain, and therefore, so that we can see the medial surface of the cut section. The first thing that we notice is this structure here. This is a sagittal view of the cerebellar vermis, which I had mentioned in my previous dissection. Just to update us about the location of the other structures so that we can orient ourselves, this is the vermis. This is the fourth ventricle, the triangular shaped structure here. This is the superior part of the roof of the fourth ventricle, what is referred to as the superior medullary velum. And this is the location of the inferior part of the roof of the fourth ventricle, which is mostly the choroid plexus, which has been removed from here. And this is the floor of the fourth ventricle, composed superiorly of the pons, and inferiorly it is composed by the medulla. So let's come back to the cerebellum. The first thing that we notice here is this branched tree-like appearance of the cut section of the cerebellum. This is referred to as the arbor vitae. It also, an arbor vitae in Latin, means the tree of life. Why is it got this appearance? It is because of the central white matter, a core of white matter with surrounding gray matter. This gives it that branched tree-like appearance. Now here there's a quick word of embryological significance. Normally in the developing neural tube, the gray matter is inside, the white matter is outside. So how is it that here the gray matter happens to be outside and the white matter happens to be inside? It is because of, during embryonic life, during development, the cells, the developing neuroblasts, which are located deep inside the developing cerebellum, they migrate outwards. And that is the reason why we have the gray matter outside and the deep white matter inside. So this outer gray matter happens to be known as the cerebellar cortex, and the white matter deep inside is known as the cerebellar medulla. Now let's take a look at since this is the vermis, let's take a quick look at the parts of the vermis. As we had mentioned in the previous section, in the dissection, this is the superior surface of the vermis, and this is the inferior surface of the vermis. This is the part of the cerebellar hemisphere, the right hemisphere, that we can see here. So let's take a quick look at the parts of the vermis. We see this tongue-shaped structure here, which is abutting the superior medullary velum. This is known as the lingula. This is the central lobule, and this is called the culmen. So lingula, central lobule, culmen. These three are located in the anterior anatomical lobe. Remember, this is the primary fissure. We are still on the superior surface. To continue, in the posterior lobe superior surface, we have the declive, lingula, central lobule, culmen, declive, folium. And coming to the inferior surface, we have the tuber, we have the pyramid, we have the uvula, and we have the nodule. So, these are the parts of the vermis: lingula, central lobule, culmen, anterior anatomical lobe, declive, folium, tuber, pyramid, uvula, nodule. Now, if you look at the uvula, just adjacent to that part of the cerebellar hemisphere, this is the cerebellar tonsil. Cerebellar tonsil is a lobule of the hemisphere which is adjacent to the uvula in the vermis. And the significance of this tonsil is that this is the one which herniates through the foramen magnum when there is increased intracranial pressure from the top or there is attraction from below. This is the one which causes sudden death, the so-called tonsillar herniation through the foramen magnum. The significance of this nodule is that if you look at the nodule and you follow it laterally, we see that this is the flocculus. So therefore, this flocculus and the nodule, they together constitute what I had mentioned in my previous dissection, the so-called flocculonodular lobe, which is the vestibulocerebellum, which is also the phylogenetically oldest part of the cerebellum. So these are the structures that we see in this sagittal view of the cerebellar hemisphere of the vermis. Now, in the vermis, the gray matter, as you can see, is very little. The same gray matter in the cerebellar hemispheres is much more, and that's the reason why the vermis is small and in the midline, but the cerebral hemispheres are so large and they have got a larger amount of gray matter. Before I exit from this video, I need to show you something which I had mentioned in the previous dissection. This is the location where the tentorium cerebelli was situated in real life. And this is the one which separates the occipital lobe of the cerebrum from the cerebellum. So this is the location of the tentorium cerebelli. And this place where my forceps is, this is the cerebellomedullary angle where we have the cerebellomedullary cistern located, where the CSF from the fourth ventricle drains into the cisterna magna. So these are the salient points. And finally, if I were to turn this specimen around, you see that the vermis midline continues onto the cerebellar hemisphere on the right side. So these are the structures that we are demonstrating in this sagittal view. If there are any questions or comments, please write them in the comment below. Have a nice day. Good day, ladies and gentlemen. Welcome to a third episode of the dissection of the cerebellum. This is the same specimen which I had demonstrated in my first video. Again, to bring you up to speed, this is the medulla, this is the pons, this is the midbrain, and this is the cerebellum. And as you can see, this is the middle cerebellar peduncle on either side. What I'm going to do, I'm going to take a section, a transverse section, through the pons, through the ventricle, and through the cerebellum. We want to see some of the cortex and the white matter, and we will try to see some of the deep cerebellar nuclei which are located in the deep depths of the cerebellar white matter, the so-called medulla of the cerebellum. The knife that you see in front of your camera, this is known as a Furcow's brain knife. It's made of stainless steel and it's got sharp edges on both the sides. This is the one which is used for dissecting the brain structures. So I'm going to dissect the cerebellum and the pons in front of you using the Furcow's brain knife. So this is the position, I'm holding it here, and I'm going to go axially, or I'm going to make a transverse section through the cerebellum. I'm going through the pons, I'm going through the middle cerebellar peduncle, I'm going through the cerebellum, I'm going through the cerebellar hemisphere, and I have separated it out, and there we go. So we can immediately see the fourth ventricle here. This is the part of the fourth ventricle. This is the pons in front of us. This is the basilar part of the pons. This is the tegmentum of the pons. We can see the middle cerebellar peduncle. We can see the cerebellar hemisphere on this side. We can see the cerebellar hemisphere on this side. And this is the vermis that we see here. So these are the structures that we can see. So we can clearly see how the vermis is disposed in the midline. There's two cerebellar hemispheres on either side. The pons is in front. The fourth ventricle is intervening in between. And the middle cerebellar peduncles are connecting them. Now here, this is the best place to demonstrate which are the deep cerebellar nuclei. In the vermis, imagine there's a midline going through. Here, this is the midline. In the gray matter in the white matter of the vermis, right next to the midline, we have a nucleus here, small nucleus, which is called the fastigial nucleus. This fastigial nucleus is the one which sends connections This is the one which sends connections to the vestigial reticular and the vestigiovestibular tract. If we go just to the either side of the vestigial nucleus, this region is known as the paravermis, which I had mentioned in my first dissection. This contains a couple of nuclei which are collectively referred to as the interposed nuclei, also called the globose and emboliform nuclei. Globose means round, emboliform means oval. They are also part of the spinocerebellum, and they send impulses to the red nucleus, and they send impulses to the VL nucleus of the thalamus, the so-called globose emboliform ruberal tract and the globose emboliform thalamic tract. And finally, in the cerebellar hemispheres, we can see a little bit of that here. We have the dentate nucleus, which is actually a serrated tooth-like appearance of nucleus, which is the largest part of the nucleus, and that is the one which sends impulses to the red nucleus again, and it sends impulses to the VL nucleus of the thalamus, but all of these go through the superior cerebellar peduncle, and they decussate at the decussations of the superior cerebellar peduncles. Now what I'll do, I'll try to take another section to see if we can see the dentate nucleus. As a matter of fact, we do see the dentate nucleus. This is the other half of the section which I had taken in the previous view. This is the other half. So if I turn it around, we can see that this serrated gray matter that we see here, this is the dentate nucleus here and here. This is the dentate nucleus. This is the one which is responsible for the bulk of the output from the neocerebellum to the cerebral cortex. So this is, and these output from the dentate nucleus, they crisscross in the midbrain at a place in the tegmentum which is known as the decussation of the superior cerebellar peduncles. So in this section also we can see the pons here, we can see the floor of the fourth ventricle here, we can see the vermis here, we can see the cerebellar hemispheres here, and we can notice that you can see the gray matter is outside and the white matter is inside. So this is a sagittal section, an axial section through the midbrain, through the pons as well as through the cerebellum. So that is all for the dissection for the cerebellum today. If you have got any questions or comments, please mark it at the comment section below. Have a nice day. Okay, good day ladies and gentlemen. Just to continue with a few other points, what I've done, I've taken an axial section through the midbrain. Unfortunately, during the separation from the cadaver, the other half of the midbrain had been destroyed, so we have only this half of the midbrain, namely the left half. So I've taken an axial section. What we can see, these are the following structures we can identify. This, what you see here in front of you, this is known as the crus cerebri of the midbrain. This contains the corticospinal, the corticobulbar tracts, and the frontopontine and the temporopontine tracts. Just behind that, you can see a pigmented area here. This is the substantia nigra, which is part of the basal ganglia, which is part of the extrapyramidal system, and this is the one which is degenerated in Parkinson's disease. If you look, the same thing will be present on the other side also, but as I said, unfortunately, it has been destroyed while removing it from the cadaver section. If you look posterior to this whole area that we see here, this is known as the tegmentum of the midbrain. And the tegmentum of the midbrain, if you look at the middle of the tegmentum, this portion, this is known as the decussation of the superior cerebellar peduncles, which I had mentioned in my dissection of the cerebellum, where I mentioned that the fibers which are coming out from the dentate nucleus, they cross over to the opposite side, and therefore this decussation of the superior cerebellar peduncles is where the crisscrossing takes place. To continue with our story, if you look at this small opening here, this is the aqueduct of Sylvius. And just behind the aqueduct of Sylvius, you can see two small globular swellings. They are respectively the superior and the inferior colliculi. Around the aqueduct of Sylvius, we can see a little bit of gray matter here. That is the periaqueductal gray matter. And in just anterolateral to them, we have the CN3 oculomotor nuclei, and we have the CN4, the trochlear nuclei, depending on whether the section has gone through the superior colliculus or whether the section has gone through the inferior colliculus. So these are the structures which I wanted to show to you in a dissection of the midbrain and how it is related to the cerebellum. Have a nice day.